talk, and it's going to be relatively in-depth. So tricky combination to get both those properties in the talk, but we're going to see how we do. A few weeks ago, I gave a Rust WebAssembly workshop to the New Orleans developer community where I live in New Orleans, USA. And someone asked me a really good question. They asked, how does async Rust work when you're running it inside the web browser? And I said, I have no idea, but I'm going to come back in a couple of months and I'm going to give you a good answer. He's not here in Hong Kong. He's still in New Orleans, but this is my mission was to figure it out. And so I figured that if I agreed to give a talk about it, then I would have to learn it before tonight. And so I did. Hello, I'm Adam. I used to work at Cloudflare where I built security products for them. I now work at a startup called Zoo. We're making CAD software. I'm going to be talking more about that at Rust Asia tomorrow. And I also blog about programming at adamchalmers.com. I wrote a little thing about Kubernetes a while ago. So if you want to complain about, tell me I'm wrong about everything, you can just go to any Hacker News thread from my blog and you can comment there. That's when people try to reach out to me. So we're going to make this quick. So let's get into it. What is WebAssembly? For a long time, JavaScript was the way you could make your browser do things besides show text and images. This made a lot of people very happy, and it made a lot of people very mad as well, because then we had to learn JavaScript. It's a great language, given that it was designed in like 2 weeks. But it's maybe we should have other languages as well. You can generally run other languages on the computer. It's weird that you can only run one language inside the browser, but not anymore. We now have WebAssembly. Your browser basically has a really tiny VM built into it now. Almost every browser does. And it's a really, really tiny, shitty language of like 20 instructions. No one wants to write it by hand, so instead you compile other languages to it. You can compile most languages these days to WebAssembly, and then you can run it inside the WebAssembly VM inside your browser, and suddenly you can write Python or C or Rust or Go or Java, anything, and you can compile it to WebAssembly and put it in the browser. And now, if you don't want to write JavaScript, you don't have to. If you want to write JavaScript, you still can. That's fine. Yeah, sure. There used to be a photo of me on that slide, but I figured I'm here in person, so you can just look at my actual face in person. So that's what WebAssembly is. Rust, I think Orhan already gave you a pretty good intro to Rust there, but async Rust is like many other languages. There's an async capability inside Rust. Asynchronous basically lets you, it doesn't let you do multiple things at once. It lets you wait for multiple things at once. If you only have one CPU core, you can't really do multiple things at once. But if you're stuck waiting for something to happen, you can put it to the side, you can pick something else up, and you can do that instead. So async is not about doing many things at once. It's about waiting for many different things at once. When one of them is ready, you can then pick it up. In Rust, async code runs in this type called a future, which represents a computation that you're waiting on. And if you're trying to do something, you're waiting for it, you can check to see if it's done. That's called polling. You can combine it with another future to make a bigger future, like say, I need one of these three things to happen, or maybe I need all of these three things to happen, so you can compose futures together. And you can await it. You can say, okay, I'm done. I'm like sick of polling it every 10 seconds. Just wake me up when it's done. So waiting is like polling until it finally works, or the computer crashes, I guess. In Rust, they compile very efficiently, very nice, quick code, blah, 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 blazing fast, blah, blah, blah. The one interesting wrinkle about async Rust is that Rust doesn't come with an async runtime. It defines the capability for async. It gives you an interface, but then you need something to actually schedule these tasks to say which tasks should get pulled when, how are you going to run them, how do you integrate with the operating system. So there's no one runtime. And this is kind of good because a lot of different runtimes have different properties. Like, we're going to see an example of this. Some people think this is a bit weird, like every other language that does async has an async runtime. Why doesn't Rust have it? We're going to see why. JavaScript is another language. Some of you may use it. Some of you may have heard of it. It's very similar in async. You can see it basically is copied the previous slide, but replace future with promise. In JS, you don't need a runtime because JavaScript comes with an async runtime. It comes with an event-based kind of system. They've already got this runtime, so you just reuse it. JavaScript runtimes now can do async as well. So we have these JavaScript promises, we have Rust futures. Can we connect them? If you compile your Rust code to WebAssembly and you're going to run it in the browser, well, okay, the browser already has this whole async runtime for JavaScript, and you're bringing in this other async system as well. So what if I want to have async Rust code that calls an async JavaScript function? What if that async JavaScript function then calls an async Rust code? You get this kind of layering of async, 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 async different languages. So what is actually happening here? So in Rust, we have the futures that represent computations. These are a trait. A trait is like an interface in Java or Go. It's not a specific type. It's kind of a contract. It's a family of types that all work similarly. So if you're working with WebAssembly in Rust, there's this JS system crate. This basically gives you a way to do JavaScript code from inside Rust. So you can define, you can say in your Rust code, browser is giving me a bunch of JavaScript functions like console.log or window.alert, and it's giving me these types that I can use, like JS number types, JS string types, JS closure types. And you can construct these values from Rust, and you can pass them around, you can send them back to JavaScript. This is how Rust can interoperate with other languages as well. And other languages also have JavaScript bindings for them. So we have a JavaScript binding for all kinds of JavaScript types that you can get in Rust. One of these types is the JavaScript future type. JavaScript promise type, sorry. So you can, read your JavaScript promises from Rust, and we can even implement traits on those. So you can convert your JS promise into this new type called JS future. And this JS future is just a JS promise that's wrapped up, and it implements the Rust future trait. And this trait is how you get to use awaiting and polling and everything. So you can now await a JavaScript promise from Rust. So how do you actually do this? You've now got this future, but there's no runtime within Rust. What do you do with it? Well, we're going to basically reuse the browser JavaScript runtime. There's no point having these two different runtimes, because when would one runtime know when to switch over to the other one? They would be duplicating resources. They would be mismanaging things, coordinating between them. It's not a good idea. Basically, there are two ways to call one of these bridged future types. You can send it back to JavaScript. You can take your Rust future, any Rust future really, and you can convert it into a JavaScript promise and send it back to JavaScript. It's now JavaScript's problem. JavaScript can choose, the JS code can choose to await it or to do some kind of like promise.all on it, compose it with other ones. That's fine. It's in the JS, it's not my business anymore. Or you can pull it from Rust, right? Your Rust code may want to await something. What happens when you do that? There's another crate you can pull in called WASM bindgen futures, and it defines its own tiny little async runtime. Kinda. There's a spawn local function in that library, and it runs the future to completion, right? Great. So end of story, right? Okay, cool. We figured it out. But what does that spawn local actually do? Because we said that there can't be two runtimes, right? So what's actually happening under the hood? I took a look at the source code, and here's my best understanding of it. If anyone here is a maintainer of Rust bindgen futures, please correct me if I did anything wrong. But there's basically a very simple queue inside this library. It's just a static global queue so that any kind of your threads can read it. And the queue contains Rust futures that should be run. Any kind of future. It doesn't have to be a JavaScript future. This means that you can pull in other Rust async libraries. I have no idea they're even running from WebAssembly or JavaScript World. And you can put them into this queue as well. So then we take this Rust future type. And we've already said you can convert a Rust future into a JavaScript promise. So we do that. We just convert it into a JS promise. And then we send it back to JavaScript. This is a little more involved than it sounds, because you have to... I learned that JavaScript has not only promises, but it also has micro tasks. I didn't even know the word tasks, but there's this thing called a micro task, which is I guess a way for JavaScript to avoid too much context switching between different events that come up. I don't know. I'm not a scheduler, but the Rust mini async runtime basically also needs to make sure that the JavaScript runtime doesn't get starved. So you can't have the Rust part kind of just pushing a billion things and then the JavaScript side gets starved out. So it honors the contract from the JavaScript side that if you have a micro task, it should get to run when it needs to, blah, blah, blah. Yeah, and this way you only have one runtime. So all of the kind of tools you're used to working with in JavaScript can still run. You can still look at the web console and you can see all these values because they are ultimately being driven by JavaScript in the end. So is this good? I think it's good. We said before that Rust doesn't have a single async runtime, and this sometimes makes people mad. But I think this is a great strength because ultimately, when you're trying to do async, you need to have some way to wait and some way to know when to stop waiting and start doing stuff again. And that is going to require some kind of primitives that you call into, right? Rust can't have an implementation of every OS's primitives because people are always making new OSs. And some things on OS and you still want to run code on them, right? So it's great that you can reuse a system like JavaScript and you can just kind of make the Rust async, use as its implementation JavaScript's async runtime. This is great. Zed, the new GUI-based editor, sorry, Orhan, it's not on the terminal. It's a windowed application. It reuses Mac OS's built-in concurrency and scheduling stuff. So Mac OS has a whole global central dispatch. Global central dispatch? Yeah. And there's no point building your own separate async world on top of that. Mac OS already should kind of take responsibility for that. So it's great that you can then take the general async interface of Rust and make its implementation just call into the one that your OS gives you. Same with embedded. Someone blew my mind recently by telling me that in our software code, where everyone's getting into async, but we need to write async code because the operating system kind of has synchronous interfaces. But that's actually bullshit because beneath that, there's just async hardware as well. The hardware itself is actually asynchronous, and so why go through this synchronous layer? Just go straight down and use the async hardware that you're given. So Embassy can do that. Cool. Thank you so much. This was a lightning talk, so it's very short, and that's the end of it. Thank you very much.
Questions? Yeah. Any questions to Adam? I thank you for your talk. I'm not sure is this the best place to ask because personally I'm writing some application in Rust that are basically the same code base for both Wasm, so browser app, web app, and native app. And one, most of the code can be like done, because Rust can compile the Wasm and etc. I can just use the same code for most of the things. But there's one thing that initially kind of puzzled me, initially kind of puzzled me is that because my application is for computer graphics and needs to be as performant as possible, but running on web app and native, some of my code need to be asynchronous, and I faced a problem that's like things that only problems that only exist on web app because the browsers only has a single its runtime, async runtime is only a single threaded, and there will be deadlock on the browser, but it has nothing in the native app. And I'm thinking, is there any effort or any solution, simple solution working that's kind of reduces or explicitly have any sort of solution or interfaces to avoid these kind of things, like just stating certain functions that's for blocking or waiting code, waiting asynchronous code, and that works on both native and web app. Yeah.
Yeah. So I've run into this a couple of times myself. Actually, I think the best approach for right now would probably be that in your desktop app, you don't have to use multiple threads in it. If you're using something like Tokyo, which is a standard kind of desktop enterprisey Rust async runtime, you can run it on a single thread. It doesn't have to use multiple threads. It does by default, but you can run it on a single thread because, like I said, async is about waiting for many things, and a lot of embedded hardware only has one thread, so why assume it? So obviously, if you kind of limit your desktop software to also use one thread, then you'll discover very quickly if you assumed the presence of multiple threads, and at least that way you kind of can bring your two implementations, make them similar. But perhaps you don't really want to limit your desktop throughput just to make the WASM throughput more easily testable. You could maybe conditionally compile your desktop app to use one thread or many threads, depending on how you run it.
Yeah, I'm doing it right now.
Yeah,
So
cool.
conditionally compiling
Yeah.
for different targets.
The other thing is that WebAssembly did just land support for threading, and this is like WebAssembly is interesting because it's evolving really quickly. It's kind of started off very simple, and they're always evolving it. So there are now thread support in WebAssembly. I don't yet know if that's. I haven't played with it myself, but yeah, maybe in a year's time you'll wake up and that problem will just never happen again.
Thanks.
Any other questions? Cool. Thank you so much. I'm talking tomorrow at Rust Asia. I'm giving a talk about what we do at zoo.dev and also doing a workshop. So if you want to know how to use WebAssembly to run other languages on the front end, you can come along and we're going to do a 2-hour kind of guided tour of how to get WebAssembly working, Rust to WebAssembly and bridging with JavaScript. So come along to that if you want to get hands-on and practical experience. Here. Where?
Just downstairs. So when you came in the door, instead of going to the elevator on the left, you would just turn right and go down the stairs. rustasiaconf.com/schedule. You'll see a whole schedule there. But it's about 9 o'clock, I believe, 8 o'clock, 9 o'clock. Okay. She's the boss. I just doing all the work. So, well, she's actually doing all the work. I'm just pressing buttons over here. Great idea. Next time.